Hi everyone. So let us continue our discussion around an application of an annuity when we are trying to save money and the specific way in which our payments were made were in terms of withdrawals. So we looked at two cases, and I'm just going to revise the two cases very quickly. So case one, if you all remember, case one was where I made an unlimited, not an unlimited, sorry, where I made a limited amount of withdrawals. So I withdrew a limited amount at a constant rate. So the amount that I withdrew did not change, and I withdrew that for a fixed period of time. And then I showed you that if I was starting at T naught and I start making these withdrawals at T1 to Tn, then I have here n equal withdrawals at some interest rate. Okay, the first withdrawal takes place at T1, the last withdrawal takes place at a Tn. Okay, the lump sum that I need to deposit now in order to fund these n withdrawals is X, and the way in which I showed you to do that is just the normal present value of an annuity. So the way in which I work this out is PTAN at I. Okay, as simple as that. So the amount that I need to deposit one time period before the first withdrawal, the amount that I need to deposit one time period before the first withdrawal is the present value of the annuity, and that is how I calculate it. Okay, and this formula holds when my withdrawals are equal and they are limited. Okay, they do not go on forever. Okay, and then the last thing is at the point where I make the last withdrawal, I deplete the amount that I have in my account. I have nothing left to withdraw. So at Tn, I'm left with 0. And then the second case, which was case 2. So case 2, I had limited withdrawals, but now these withdrawals were increasing. So they're limited withdrawals at an increasing rate. Okay, so again here, I'm withdrawing from my account for a fixed period of time, but the amount that I'm withdrawing is increasing from withdrawal to withdrawal. So this is called a growing withdrawal. Okay, it's a growing annuity, right? So it's a growing annuity. So if I am starting at, if I start at T naught, I make the first withdrawal at T1, make the second withdrawal at T2, but now this withdrawal is increasing at some growth rate. Okay, and up until Tn, I make a withdrawal 1 plus R to the n minus 1. Okay, where I is my interest rate, R is my growth rate. Do not forget that the period when the interest rate and the growth rate need to match the time period when I am making withdrawals. Okay, that still needs to happen. And how do I work out now the lump sum that I need to deposit in order to fund these n increasing withdrawals? Okay, these withdrawals are now increasing. How do I do so? To work out the value of X here, I work out the present value of a growing annuity. That X there, the lump sum that I need to deposit at T naught in order to fund these future growing withdrawals is the present value of a growing annuity. We've done this already, so that is PT 1 minus 1 plus I to the minus n, 1 plus R to the n, divided by I minus R. So to find the amount that lump sum that I need to invest now, I can work out the present value of a growing annuity. Now let us extend this to case 2 and to case 3 and case 4 rather, where we no longer have a limited amount of withdrawals. We have withdrawals in perpetuity. Okay, and perpetuity means that these withdrawals go on forever. Okay, so let us then move our attention to case 3. So case 3 is when I make an unlimited amount of withdrawals. So I make unlimited withdrawals. Remember, this means then if I'm making unlimited withdrawals, it means that n tends to infinity. The number of withdrawals that I make is able to become infinitely large. Okay, which means that it's happening in perpetuity. Okay, but these unlimited withdrawals are taking place at a constant date. Okay, so what is case 3? I'm withdrawing the same amount but for an unlimited amount of time. I'm able to withdraw it forever. So let us try and depict that onto a timeline. So I start at T0. At T1, I make the first withdrawal. At T2, I make the next withdrawal. Up until Tn, I make the next withdrawal. But then it continues to Tn plus 1, make the next withdrawal, and so on. It continues forever. So now I have n that tends to infinity. I don't know what that n is because n is getting infinitely large. I have n that tends to infinity, but these withdrawals are equal. Okay, they're equal withdrawals. And these withdrawals are made in perpetuity. Perpetuity meaning that they go on forever. Okay, now the question is, how do I work out the lump sum here? How do I work out the lump sum here that I need to deposit to fund an unlimited amount of withdrawals for perpetuity? What do I need to deposit now so that for the rest of my life I'm able to fund my income? How do I do that? That is what we need to try and figure out. Okay, the way in which I do so is I take the limit, remember limits now, I take the limit as n tends to infinity of the present value of an annuity. Okay, so if I do that, I take the limit as n tends to infinity of, and remember what the present value of an annuity is, it's pt 1 minus 1 plus I to the minus n divided by I. Now, this goes back to your understanding of limits from differential calculus. What happens as I make n infinitely large in this term here? Remember, pt is just a number, so I can take it in front of the limit. So all I need to do is evaluate this bit here. I'm not going to do it for you, but what I'll show you is that if I make n infinitely big there, if I make n infinitely big, this term here tends to 0. That term there tends to 0. And so what am I left with? I'm left with pt over I. And this is the present value of an annuity in perpetuity. Okay, the present value of an annuity in perpetuity is just equal to the payments, the value of the payments divided by the interest rate. That's all it is. Okay, and that is the formula. If I rearrange that formula, it means that PT is equal to I multiplied by PV. Okay, if I rearrange the formula. What does this mean? What does this mean here? It means that my income depends on just the interest rate, which is I, and my capital only. Okay, my income depends on those two things. My income is my payments, right? My payments just depend on these two things, and it's as simple as just working out that. So the present value in perpetuity when I make constant or equal withdrawals for an unlimited amount of time is just the value of my payments divided by the value of my interest rate. So this here, whatever this is the amount that I require now. That's the amount that I require at T naught in order to fund all of these future withdrawals in perpetuity. Let us now consider the last case, which is case 4, and it's fairly obvious what this case is. We are going to make an unlimited number of withdrawals. So what does that mean? That means that the number of withdrawals that I make tends to infinity. And what do I mean by n tends to infinity? Well, quite simply put, it means that I cannot determine what n is. The number of payments that I make or the number of withdrawals that I make in this case, I cannot determine it because it goes on in perpetuity. Okay, so we use this word perpetuity as a synonym for infinity. Okay, it goes on forever. Okay, so we make unlimited withdrawals at an increasing rate. So what is this case? We've got growing withdrawals that are taking place in perpetuity. So if I start at T naught, I make the first withdrawal at T1, I make the second withdrawal at T2, but this withdrawal is growing. The nth withdrawal I make is growing at 1 plus r to the n minus 1. The n plus 1th withdrawal that I make is growing at a rate of 1 plus r to the n, but these withdrawals go on for infinity. So here now I have n that goes to infinity, increasing because the withdrawals are increasing at some growth rate r. They're increasing, they're unlimited because they go on forever. Okay, and these are now the withdrawals that I have. And the question that I have now is, what is this lump sum that I need to deposit today in order to fund an unlimited amount of withdrawals that are growing, that is going to fund my income for perpetuity? That is the question. So let's again go back to the definition of limits. So now I'm going to take the limit as n tends to infinity of the present value of a growing annuity. Okay, if I work that out, that's the limit as n tends to infinity. We know what this is. It's pt 1 minus 1 plus I to the negative n, 1 plus r to the n divided by I minus r. Now, if I make n infinitely big, this term tends to 0 and this term tends to 0. So this entire thing here is 0. So what am I left with? I'm just left with that bit there. So that's equal to pt I minus r. And what that is, it's the present value of a growing perpetuity. So when I have an unlimited amount of withdrawals, but those withdrawals are increasing, the way in which I work out the lump sum that I need to deposit now is very simple. It's the amount that I'm going to withdraw divided by the interest rate minus the growth rate. Okay, so there's one important bit here. This here, I minus R needs to be greater than 0, which means that the interest rate must be greater than the growth rate. So when you're doing case 4, when you're doing unlimited withdrawals at an increasing rate, you need to check that your interest rate is bigger than your growth rate. Okay, now that I've explained case 3 and case 4, we can then complete B of the second part of the question and B of the first part of the question, and as well as B of the second part of the question. So let us just go through the wording of the question again very quickly. So remember that this person wanted to retire on his 50th birthday, and he's 29 now, and he wants to make consecutive equal monthly deposits of PT into a savings account on his 30th birthday. So he starts at T1 is when he makes the first deposit, and that's when he is 30. The question is, what is the value of T when he is 50, meaning how many withdrawals does he make? I showed you how to do that. From 30 to 50, there are 20 years. 20 multiplied by 12 is 240 months. Okay, 240 months means I have 241 payments or deposits. So that was T241, and in total here, N is equal to 241 monthly deposits. If he's making deposits monthly, I need I12, which was given there as 0.75% per month. Then the question goes on to say that immediately after his last deposit on his 50th birthday, which means there at T241, the man will use all of the money in his savings account. So all of the money in his savings account is the future value of his savings annuity. Okay, and what he's going to do to that is he is going to purchase a retirement annuity. And I explained what a retirement annuity is. It's an annuity where you make a lump sum deposit at the beginning and you make withdrawals at regular points in time thereafter in order to fund your own income. Okay. Um, Given that the retirement annuity will earn interest at a rate of I star 12, which is equal to 1% per month, calculate the value of the man's monthly deposits PT. We've already done this one. We've done this one in class. Calculate it if the retirement annuity will pay the man 1,000 Rand. So that's PT star every month. So if his retirement annuity is monthly, I need the corresponding monthly interest rate. So it is a simple annuity starting 1 month after his 50th birthday in perpetuity. So that is the first question that we need to answer. And the second one says, find the value of the man's monthly deposits if the first payment of the retirement annuity is 1,000. But in order to account for inflation, the payments from the retirement annuity will increase from the second payment onwards at an effective rate of 0.5% per month. So R star 12 is 0.5% per month. All three things match here. The time when I make withdrawals matches the interest rate, which matches the growth rate. Okay, so it's clear that this is case 3, okay, because here I am making a limited amount of withdrawal, an unlimited amount of withdrawals, but those withdrawals are constant, okay, and this one here is case 4, because I'm making an unlimited amount of withdrawals, but these withdrawals are increasing. Okay, I'm going to do both of those questions for you. You need to go and do this entire example again for yourself. It is a very important example because it encapsulates all 4 cases of the withdrawals. Okay, so let's look at the timeline now. So let's first look at the timeline of his savings annuity. This is the savings annuity. Now, so remember the savings annuity has N equal to 241 equal monthly deposits of PT, right? And because the deposits are monthly, I need the monthly interest rate, which I have. Okay, and then remember that the future value of this annuity, the future value of the savings annuity takes place when I make the last deposit, which is at T241, and that is equal to PTS T41 at 0.75%. That is the amount in his account. That is what the amount in his account should be at this point. Okay, and remember that this amount here, whatever this amount is the lump sum that he deposits into his retirement annuity. So the second timeline is his retirement annuity. So his retirement annuity is an annuity in perpetuity because I am making n tending to infinity equal equal monthly deposits, or sorry, withdrawals rather, of PT star, that's PT star, which is equal to 1,000. But these are happening in perpetuity. It's going on forever. Okay, it's going on forever. Okay, so at T naught, at small t naught, which corresponds to big T241, I have the present value of an annuity in perpetuity. Okay, and remember the present value of an annuity in perpetuity is equal to the value of the payments divided by the corresponding interest rate. Remember that payments are taking, deposits are taking place monthly, so I need the monthly interest rate. So this is equal to 1,000 divided by 1%. Okay, and what's important to note here is that at T241, at this stage here, which corresponds to small t naught, the future value of my savings annuity is equal to the present value of my retirement annuity in perpetuity. Those two things are the same, and so I'm going to use the fact that I know this in order to calculate what the value of his deposits need to be. Okay, so the first thing is that you should notice that at big T241, which is the same as small t naught, the future value of his savings annuity coincides with the present value of his retirement annuity in perpetuity. Now we've already formulated these on the previous page. His savings annuity is PTS241 at 0.75%. These deposits are monthly, so I need the monthly interest rate, and that's equal to the present value of his retirement annuity in perpetuity. Remember, that is just the value of the payments divided by the interest rate. The value of the withdrawals was 1,000 divided by the interest rate, which was 1%. That's all that needs to happen in this question. Okay, and 1,000 divided by 0.01 is 100,000. So what is the 100,000 now that we've worked out? The 100,000 that we've now worked out is what he needs. This is the lump sum that he needs to deposit into his retirement annuity. And this 100,000 needs to also be the amount in his account in his savings annuity. Okay, and knowing that now, we can use the compound function on our calculator in order to find the value of those payments. So if you go to your calculator, your financial calculator, you need to put n equal to 241. The interest rate is 0.75. The present value is 0. The payments is what we need to solve for, and the future value is 100,000. Okay, and if you solve for the payments, you should get the payments equal to, you should get PT equal to 148 Rand and 39 cents. Okay, what is this here? What is this? These are the deposits that the man needs to make from his 30th to his 50th birthday in order to guarantee that he gets a monthly income of 1,000 Rand in perpetuity when he retires. Okay, let us now look at the last example, which corresponds to case 4. The payments made, or the withdrawals that I make from the retirement annuity increases from the second withdrawal onwards at a rate of 0.75% per month. So that is R star 12 in perpetuity. So I'm making these withdrawals in perpetuity, but the withdrawals are increasing. So that is case 4. So let us now structure our timeline. Again, let's first look at the savings annuity. So there's his savings annuity. I'm not going to redo it. The savings annuity is not changing. The savings annuity has these n equal to 241 monthly deposits at a monthly interest rate of 0.75%. And so the future value of his savings annuity takes place at T241 and it's equal to PTS241 at 0.75%. Okay, now let us look at the retirement annuity. This is where there are changes that are taking place. So this is his retirement annuity. What is happening in his retirement annuity? He makes a first withdrawal at T1. Okay, and the first withdrawal at T1 is just the value of the payment. It's just PT star. But what happens from the second withdrawal onwards? Those payments are increasing at this monthly growth rate. Why is it a monthly growth rate? Because I'm making the withdrawals monthly. But these withdrawals happen in perpetuity. Okay, so how many withdrawals are there? N star tends to infinity. There are N star tending to infinity growing withdrawals. Okay, remember the withdrawals are growing at the growth rate. They are growing with monthly withdrawals, right? If the withdrawals are monthly, I need a monthly interest rate and I need a monthly growth rate. Okay, they are monthly withdrawals that happen in perpetuity. They happen forever. Okay, and now the question is, what is the lump sum that he needs to deposit at this stage here? What is the present value of the growing retirement annuity in perpetuity? It's a bit of a mouthful. How do I work that out? We structured it in the previous slides. It's PT star divided by I star 12 minus R star 12. The first thing you need to check is I star 12 greater than R star 12? If you look, 1% is greater than 0.5%, so that condition is true. So how do I structure this? It's PT star, which is 1,000, divided by I star 12, which is 1%, minus R star 12, which is 0.05 or 5, not 0.05, 0.005, which is 5%. And in the next slide, I will show you how do I find the value of the deposits, how do I find the value of these deposits that he needs to make if this is the structure of his growing annuity. So one thing you should notice is that at this point here, the future value of his savings annuity coincides with the present value of his growing retirement annuity in perpetuity. Okay, so the first thing you should note is that at big T 241, which is the same as T naught, the future value, I'm making the same mistake, the future value of his savings annuity should be the same as the present value of his growing retirement annuity in perpetuity. Now we've already found out what these entities need to be. The future value of the savings annuity is PTS241 at 0.75%. The present value of this growing perpetuity is PT star over I star minus R star, which was 1,000 divided by 0.01 minus 0.005. Okay, and if you work this out here, you should get 200,000. So what is that 200,000? The 200,000 is the lump sum that he needs to deposit into his retirement annuity in order to make an unlimited amount of growing withdrawals in perpetuity. Now, those 200,000 needs to be the same as the amount in his account in his savings annuity, and that is what this equation is saying. If he needs to have 200,000 in his savings annuity after making 241 monthly deposits at an interest rate of 0.75% per month, what are the value of those deposits? So if you go to the compound function on your calculator and take n equal to 241, I equal to 0.75, the present value is 0, the payments is what I'm solving for, and the future value is equal to 200,000, you should get the value of the payments to be equal to, or approximately equal to 296 Rand 78. So what is this amount here? That is the deposits that this man needs to make from his 30th to his 50th birthday in order to guarantee that he gets a monthly income of 1,000 Rand that grows at a rate of 0.5% per month in perpetuity when he retires. Okay, and so that is the end of example one. I want you all to take some time to redo the entire example one and understand the structure of each of the four cases when we are dealing with withdrawals. So I will summarize them for you on the next slide, and I want you all to use this example as a basis for your understanding for this section. So let us summarize. Okay, for case one, let's do case one. For case one, remember I have limited withdrawals at a constant rate. Okay, and the way in which I find the present value of an annuity is the same as how we've been doing it all along. It's PTAN at I, which is PT 1 minus 1 plus I to the negative n divided by I. Then case two is I have a limited amount of withdrawals, but these withdrawals are at an increasing rate. Okay, the withdrawals are increasing. The way in which I find the lump sum that I need to deposit today is the present value of a growing annuity, which is PT 1 minus 1 plus I to the negative n multiplied by 1 plus R to the n divided by I minus R. Okay, then the next case is case 3, which is an unlimited amount of withdrawals at a constant rate. So how do I find the present value? How do I find the lump sum that I need to deposit now in order to withdraw an unlimited amount, an unlimited equal amount of money for perpetuity? We call that the present value of an annuity in perpetuity. And the way in which I do that is it's the value of the payments divided by the interest rate. And then the last one is case 4, which is I'm making an unlimited amount of withdrawals, but these withdrawals are growing. And the way in which I work out the lump sum that I need to deposit now in order to make an unlimited amount of growing withdrawals in perpetuity is by working out the present value of a growing perpetuity. And the way in which I formulated that was the value of the payments divided by the interest rate minus the growth rate, provided that the interest rate is greater than the growth rate. And so these four cases encapsulate the four cases of solving for the deposits when these deposits are withdrawals.